A plastic wheel. A 42 centimeter diameter wheel consisting of a rim and 6 spokes is constructed from a thin, rigid plastic material having a linear mass density of 25 grams per centimeter. This wheel is released from rest at the top of a hill 58 meters high. Part A, how fast is it rolling when it reaches the bottom of the hill? Part B, how would your answer change if the linear mass density and the diameter of the wheel were each doubled? So this is our wheel. We have 1, 2, 3, 4, 5, 6 spokes, and we have radius r, and we have also the rim. Now, the diameter of the wheel was given, so 2r is equal to 42 centimeters. Therefore, the radius of this wheel is 21 centimeters. Now, for the rim, which is the circumference, we have a total length which is equal to the circumference. The length of the ring L sub r is equal to 2 pi times the radius, so that's going to be equal to 42 pi centimeters. The mass of the rim, on the other hand, will be equal to the mass density 25 grams per centimeter multiplied with 42 pi centimeters. This gives us 1050 pi grams for the mass. Okay, now we have 6 spokes. The 6 spokes, they each have a length m is equal to lambda times r, which is 25 times, because they each have a length which is equal to the radius 21, which is 525 grams. And we have in total 6 spokes and the rim to consider. All right. So the moment of inertia for a uniform ring was calculated in problem 9.48. It's equal to the mass of the ring multiplied by the radius square. The moment of inertia of a uniform rod was calculated in problem 9.73. It is mass of the rod length squared divided by 12. Now we have a different situation here. This is one of our spokes. We know the moment of inertia for center of mass, but the pivot is at one end. So you can see here the pivot is at one end of this uniform rod. So that's the pivot. So in that case, we have to use the parallel axis theorem. The moment of inertia for the edge, rotations about an edge, will be equal to I center of mass plus m L squared over 4 L squared over 4. Why? Because the distance between these two rotation axes is equal to L over 2. Okay, so it was I center of mass plus md squared. So therefore we see that this moment of inertia for rotations about an edge of the about one end of the uniform rod will be equal to ml squared over 3. This is our parallel axis theorem. Okay, so for each spoke, I spoke, we have mr squared divided by 3, because the length of each spoke is equal to 1 radius. So this is the contribution for each of them. Now the total moment of inertia, I total, will be equal to the uniform ring moment of inertia with respect to the center, mr r square, plus 6 times the contributions from each spoke, mr squared divided by 3. So we have in total, in r squared parentheses, because this 6 will become 2 simplified by 3. So we will have r squared parentheses m sub r, the mass of the rim, plus twice the mass of each spoke. And the total mass we have here, m total, will be equal to mass of the rim plus 6 times the mass of each spoke. Okay, so let's start with part A. This is on top of a hill, 58 meters high. It is released from rest. How fast is it rolling when it reaches the bottom of the hill? So we have an initial potential energy, U initial, equals to the total mass, M total, GH. This is mass of the rim plus 6 times mass of each spoke, GH. The final potential energy will be 0. The initial kinetic energy is 0 because we have a released system. And final kinetic energy will be the rotational kinetic energy, 1/2 I total omega squared, plus the translational kinetic energy of the center of mass, 1/2 m total v center of mass square, where v center of mass is equal to omega times the radius. Okay. So if we write energy conservation here, because we don't talk about any non-conservative forces, we have a mass of the rim plus 6 times the mass of each spoke, GH, U initial minus U final, will be equal to delta K, which is K final minus K initial, 1/2. For I total, we have r squared mr plus 2m. So this is what I'm substituting for I total here, multiplied with omega squared, but omega is v center of mass over r, so v center of mass squared divided by r squared, plus the translational kinetic energy, 1/2 total mass, mass of the rim plus 6 times the mass of each spoke, velocity of the center of mass squared. So we have a simplification here. These r squareds will cancel. So what I have written here is minus delta U is equal to delta K. That's conservation of energy. Okay, so this leaves us with, so you can see here we have mr plus 2m, mr plus 6m, so 2mr plus 8m divided by 2, this becomes mr plus 4m, v center of mass squared. So we find that the center of mass speed, final center of mass speed, will be equal to mass of the rim plus 6 times mass of each spoke, GH, divided by mass of the rim plus 4m square root. Okay, so now we can substitute the numbers here. The center of mass final speed will be mass of the rim was calculated here. It is 1050 grams. So 1050 pi grams plus 6 times mass of each spoke was 525 grams times 9.8 meters per second square times 58 meters where it was released divided by mass of the rim 1050 pi grams plus 4 times 525 grams, and each of these grams can be converted to kilograms by multiplying with 10 to minus 3, but that doesn't change anything, so we can keep them as grams if you wish, because the units are cancelling. So this gives us finally 26.0 meters per second. So this is our final center of mass speed. What is the final angular speed? The final angular speed will be V center of mass divided by R V center of mass divided by R, which is 26 meters per second divided by 21 10 to minus 2 meters. This gives us 124 radians per second. This is our final angular speed. Now in part B, we want to know what happens if we double the mass density and the diameter of the wheel. So they're each doubled. How does the answer change? Okay, so mass of the rim was actually 2 pi r times lambda. And mass of each spoke was lambda times r. So this is what I called m in my calculation. So mass of the rim plus 6m would be 2 pi r lambda plus 6 lambda r. And mass of the rim plus 4m would be 2 pi r lambda plus 4 lambda r. Now I look at my answer board for the center of mass final speed. It is mass of the rim plus 6m gh divided by mass of the rim plus 4m square root. So if I substitute mass of the rim plus 6m is actually in r lambda parentheses 2 pi plus 6 lambda r, then we have gh divided by 2 pi plus 4 lambda r, and as you can see lambda r's are cancelling and we have square root as well. So you can see that our final answer V center of mass is actually 2 pi plus 6 gh divided by 2 pi plus 4 square root. Okay, so this is independent of the mass density lambda and the radius of the wheel, so there will be no change in the center of mass final speed. So if you double these two, there will be no change. But if I look at the angular speed is actually center of mass speed divided by r, v is equal to omega r. So if we double r, when we double the diameter, we will be doubling the radius. You can see that because the center of mass speed does not change, we will have omega would be halved. So we will have 1 over 2 times the original omega that we obtained in part A. Okay, So to summarize, we have a 42 centimeter diameter wheel. It consists of a rim and 6 spokes, and these spokes have basically a length r. It's constructed from a thin, rigid plastic material having a linear mass density 25 grams per centimeter, and it is released from rest at the top of a hill 58 meters high. So I see that the rim has a length 2 pi r, so it's going to be 42 pi, and its mass lambda times r, so you can see my lambda is 25.0 grams per centimeter. So I multiply it by lambda, I obtain the mass of the rim. And for each spoke which have lengths r, mass of a single spoke is lambda times r. For 6 spokes and 1 rim, we have to add the contribution from 6 spokes and the rim. Now for rotations, the center of mass rotation of a uniform ring is basically a mass of the ring times r squared. This was done in problem 9.48. For the uniform rod, the center of mass, rotations about the center of mass have a moment of inertia ml squared over 12. For one end, using parallel axis theorem, it is L squared over 3, but L is equal to R here for each spoke. So this is going to be mr squared over 3. Total moment of inertia will be the contribution from 6 spokes plus the rim. We have r squared parentheses mr plus 2m. And the total mass is mr plus 6m. So when this is released from rest on top of a hill, it has an initial potential energy m, total gh, final potential energy 0, initial kinetic energy 0 because it was released. Final kinetic energy will have 2 components, the rotational kinetic energy plus translational kinetic energy of the center of mass. And the center of mass is equal to, V center of mass is equal to omega times the radius. So writing this conservation of mechanical energy, so this is delta E mechanical is equal to 0, no friction. Because of that, we have only conservative forces, and writing the energy conservation, we obtain this final speed of the center of mass as mr plus 6m gh divided by mr plus 4m square root. When we substitute the numbers here, because we have ratio of 2 masses, it doesn't matter if we keep them grams or kilograms, but anyway, we obtain our final answer 26 meters per second, and then just dividing this by the radius, we obtain the angular speed. In part B, we were asked to analyze the situation where lambda and r were doubled. So looking at my answer for the speed, because these masses are calculated by multiplying lambda r with a number and lambda r's cancel, I see that both lambda and r have no influence on the final center of mass speed, so there would be no change in V center of mass. No change in V center of mass, but r is doubled, implies that the final angular speed will be half of the value I calculated in part A.